What gen is this? I don't know. I'm not a bad streamer. Okay, fine. I'll find it. Calm down. We are Team 10, and we'll be making a model to classify Pokémon generations using sprites found in the video games. Take a look at Pikachu through the ages. We have 5 classes here, each one limited to the generations that were released on a particular device. You can see a relative increase in artistic ability as well as graphics. The goal is to build a foundation for organizational automation that cannot be hard-coded. There are very unobvious features the model has to learn for it to classify sprites. Seeing how a neural net is able to interpret these features will allow us to broaden the scope of this project to even more advanced categorizations of visual data. Look at these images of Mario. A neural net built to recognize Mario may learn to find the red hat, maybe the white gloves, or even the signature M, but they are all the same image in the eyes of the network. This cannot be the case for our model. For example, all these Charizards are from different classes, regardless of the many features they have in common, so it may not be as easy as it seems. For data collection, we used a combination of web scraping and a pre-existing sprite database. Sprites from multiple games in each class were grouped to grow our dataset to almost 9,000 images, with a clear imbalance among the classes. From there, we resized all images to the largest size among our data, which prevented details from being lost in the higher quality sprites. An in-game background was then added to make the training more representative of what is seen in the actual games. To address our imbalance, we first tried augmentation, which was a combination of rotations, translations, crops, and zooms. This didn't help as much as we hoped. We then modified the weights of each class proportional to the images they contained.
Our network takes in Pokemon game sprites and classifies them based on the game console their respective game was released on. The baseline model is a 3-layer ANN with rarely activation functions in between layers. The ANN reads an array representation of a 120 by 120 RGB image and passes it through hidden layers of decreasing nodes to classify the Pokemon sprite. The display hyperparameters are not optimized as this is a baseline model. To improve results, we try implementing transfer learning with AlexNet. The AlexNet model trains a 2-layer ANN classifier on AlexNet feature representations of our dataset. These features are 256 by 6 by 6. Like the baseline, we are also using readily activation functions. The batch size of 16 was chosen because smaller batches allowed the model to learn the various art styles in the class and how they evolved over time. Likewise, a small learning rate of 10 to the negative 5 finally tunes the model to reach lower global minimums. A weight decay of 10 to the negative 5 is also introduced to prevent exploding gradients by keeping weights low. Our primary CNN model has 3 convolution layers, each of which are passed through a rarely activation function and a pooling layer. The 2-layer ANN classifier takes in feature maps of dimensions 15 by 11 by 11 and passes it through a hidden layer and a rarely function before classifying the original sprite. The same batch size is used as the AlexNet model, but the learning rate and weight decay are increased to 0.0015 and 5 times 10 to the negative 5 respectively based on results from trial and error runs. All 3 models were trained for 30 epochs for consistency, and further improvements for more epochs would not be significant as shown in later sections.
As we saw earlier, one potential application for our classifier is to serve as an auto-recognizer for Pokemon in live streams, so that categorizing the gaming hardware can be streamlined. To achieve this, we can train a YOLO V3 model to detect Pokemon in the image, and use the detected bounding box to crop the region around the Pokemon. Instead of using the plain background image, the cropped Pokemon from the image can be used and be fed into our CNN classifier since it is more realistic. By using cropped images from YOLO V3, we can also generate a new testing set with which we can verify the true performance of our model. To train YOLO V3, we'll need to generate some training data. We can manually create a dataset using Pokemon Battle Creator. This platform allows us to further augment our data by altering the background color, and this way our model can adapt to a variety of battle scene conditions.
Let's see how the model performs on previously unseen data. On the right, you can see a sample of our testing dataset, which has already been uploaded onto Collab's local server. Preliminary code has already been run to make this model functional. Firstly, let's look at the baseline model. It gets an accuracy of 27%. We expected this model to be bad because it is only the baseline. Now, let's look at AlexNet. AlexNet gets an accuracy of 68.5%, better than the baseline, but still quite bad. Finally, let's look at the CNN model. This gets an accuracy of 74%, making it the best out of the 3.
Starting with the baseline ANN, we saw relatively poor performance. 60% may not be bad for a baseline or for complicated classification problems such as this, but we can see that validation is 50% and our testing accuracy falls even lower to about 27. The Gen 1 class is often confused with Gen 2, and the higher Gens 4 to 7 are often confused between themselves. In our preliminary stages of planning, we found that this would also occur in humans, even those who consider themselves Pokémon aficionados. We can see that there are large fluctuations in the accuracy graph, showing that our hyperparameters are clearly not tuned for optimization. Performance could increase if we adjusted these and trained for more epochs, but it was not worth the time for a baseline model. The AlexNet ANN produced good accuracies in training and validation, but testing is significantly lower. AlexNet appears to have overfit on the training data, and perhaps validation data was too similar. We do see that AlexNet performs well in Gens 6/7. The accuracy curve for the AlexNet ANN plateaus at about 20 epochs, which is also where the validation loss curve plateaus and fluctuates. However, the training loss curve continues to decrease, implicating some overfitting. Last, our main CNN model. Here, we see training and validation are relatively the same as the AlexNet ANN, but the testing accuracy is much better overall, and the best of our three models. There are relatively low accuracies in the middle 2 to 5 gens, but the model does achieve perfect accuracies for Gen 6/7 in testing. As expected, the accuracy increases over each epoch. We do not see signs of significant overfitting or underfitting in these results. Here on the right, we have Pokemon classified by our network. While the model does not accurately predict all Pokemon, overall the model has better efficacy than a primitive baseline model and human identification. Some of these inaccuracies may be caused by unused sprites being used in later games or other artist inconsistencies.
Evaluating the performance of YOLO v3, there were several instances of bounding boxes being correctly detected. In some cases, more than one bounding box was identified, but this was still acceptable since the Pokemon was still enclosed in the detected area. Most of the false negatives occurred due to low contrast between the Pokemon and the darker backgrounds, as you can see. Overall, YOLO v3 was able to detect Pokemon and battle images with an 80.1% accuracy. One useful takeaway from the project is that data augmentation and increasing the dataset size is not always the right call when using an imbalanced dataset. Class weighting is an interesting alternative that can also help build on the classification ability of any model. Another topic to explore is what features are being extracted by the CNN during classification. Both the feature maps here seem to imply that as the generation number as well as the image quality increases, the model puts less significance towards edges and color contrast, and so the feature maps become less detailed. Since this is a unique classification problem, it is quite fascinating to see what the CNN picks up on, and what it learns to be important features. This discovery can help guide the development of similar classification problems in the future. Thanks for watching.